Complexity.
Okay, well, thank you. Thank you for this opportunity to connect with you guys. I shouldn't say it's lonesome in the Faculty of Economics, but it's nice to be able to be here. So I'm going to talk about choice under computational complexity. This is what I'm going to try to do in the next hour. First, I'm going to talk about two paradigms of uncertainty. My original title was Professor of Finance. I lost it in the midst of the ages. Finance is concerned with uncertainty, and I'm still concerned with how people deal with uncertainty. And I'm going to show you two paradigms of uncertainty, and one actually that's very popular across many, many fields, economics, psychology, neuroscience, and then another one that actually is less popular that you see in psychology as well. And so I can reflect a little bit on the methods, the difference in methods that are being used. Then I'll talk about computational complexity theory. Conceptually, this is very difficult if you're not familiar with it, so bear with me. I'm going to try to be intuitive here, although there's a point at which you cannot be intuitive anymore. We really have to be extremely precise. And then we'll go to the beat, that is, how do humans choose under computational complexity, and then finally how the brain deals with computational complexity. I have also something on what happens when you drug people, but that's for another occasion. All right, this should work, right?
I'm not sure I can guarantee you that that works.
No. All right. So, as I mentioned before, it actually is important to be precise in all the terms that are there. This is hardcore mathematics that I'm going to talk about today. And mathematicians tend to be very precise. We are dealing today with what is called computational complexity. We are not dealing with other terms that have been used for complexity, such as procedural complexity. In computer science, this is related to the theory of automatons. System complexity, engineering and biology is interested in that. Swarm intelligence, emerging intelligence, chaos theory, or even Bayesian inference complexity. So you'll see, hopefully by the end you will know what I'm talking about in terms of computational complexity. There is a term that I actually prefer to use, which is combinatorial complexity. Right? So let's go back and look at two paradigms of uncertainty. On the left-hand side is a multi-arm bandit problem, a two-arm bandit problem that you're probably familiar with. In the bandit task, the question is, there are two arms there, and they give you stochastic rewards. Right? They're generated by some mechanistic device, maybe some random number generator, pseudo-random number generator, but you don't know which one gives you the highest rewards. So then you have to start exploring, and the question is which arm is the best. And the uncertainty here is generated by maybe a pseudo, but a random number generator. Right? And a lot of what you see in terms of experimental paradigms in economics, in psychology, in neuroscience, is using that type of setup. Probabilistic uncertainty, I call this. On the right-hand side is a very different kind of uncertainty. It's a 0-1 abstract decision version. So you have a bunch of items. Each of these items has a value. These are $12, $14, $19. And they have a weight, 70 kilograms, 6 kilograms. And the question is, if you have a knapsack with a capacity limit of 35 kilograms, which is in the middle, in the center, right? That's capacity limit. And and you want to reach $46 in value of the knapsack. Can you do this with a subset, maybe the whole set of these items? Yes or no? And I'll give you 20 seconds, right? Or you may not want to spend more than 20 seconds on it because you have to run for the bus or whatever, right? The question, there's uncertainty as a result. Right? So the 0-1 abstract decision task is, can you reach a value of $46? And uncertainty here is generated by the combinatorial complexity. In terms of subset, there's 1, 2, 3, 4, 5, 6 items. So there are 2 to the 6 possible subsets. You can list all of them and then just try all of them. That's actually a pretty good way of doing things. But when there's 10 items, 2 to the 10th. Right? When you go to Marks and Spencer, they have about 5,000 different items, 2 to 5,000 different. And there's maybe you don't want to do that, right? So you want to do something more. But it's so when you then walk out of Marks and Spencer, and if you spend your £100, you don't know whether you actually did a good job, right? And that leaves you with this uncertainty. Maybe I should have bought something else, right? The questions in the Bandit task is that people have been asking is, do humans adapt their decision making, their effort, their choice to the difficulty at hand? So we know a lot mathematically about the Bandit problem. And we can write down the base optimal strategies here, and we ask, can you do the right thing? And the answer is people spend more effort when the problem is more difficult, whereas in terms of performance, the performance goes down. But that's exactly what's optimal. On the right-hand side, following Newell and Simon, if you go to the literature, which is not so much applied to the knapsack problem, but an equivalent problem, the traveling salesperson problem, people have been asking, what are humans thinking when they decide? Right? So you see people trying to solve it, but you can see that people think. Right? And then the question is, what are they thinking? What algorithm are they following? And that has actually not been very fruitful. We know with the traveling salesperson problem, some things. And in knapsack problems, we also know some things of what they're doing. But as you'll see later on, there is an enormous amount of heterogeneity there. Right? So I'm going to turn around this paradigm. So rather than following Herbert Simon and Newell and just trying to figure out what's going on in people's minds and asking them, what are you thinking? I'm an economist, I don't ask questions. Right? I think that people lie. That's a joke, by the way. I'm going to actually try to turn it around and turn it into the equivalent questionnaires on the Bandit task. And that's what I'm going to try to show today, that this actually has been very fruitful, at least as a beginning to try to understand what people are thinking. Modeling uncertainty in the Bandit task, information that's given to the participants is such that you can actually set up what they call in probability theory an ergodic experiment that can identify unique probabilities that the correct arm is left. So an objective probability that says that the left arm is correct with 40% probability or something like that. So we can, an ergodic experiment just means by repeating, by sampling, by just doing a very stupid exercise where you don't have to think, you just draw, right? And you see what happens by reinforcement learning, by stuff that Silicon Valley does, ChatGPT, reinforcement learning, just randomly, not thinking about anything. You can actually find objective probabilities. It's extremely powerful because now if you do an experiment, as an economist, psychologist, you have a benchmark. These are these objective probabilities, and then you can see whether the subjective probabilities and the choices are related to that. Here, the knapsack task, it's a deterministic problem, right? Without strong restriction on how these capacities, values, and weights are drawn, you can set up an ergodic experiment that allows you to determine the objective probability that the instance is satisfiable, that is the technical term, that the answer is yes. In fact, that particular instance, the answer is either yes or no. And you can try whatever you want. Eventually you'll find out that it's always yes or always no. Right? So as a result, there do not exist objective probabilities against which participants' subjective beliefs can be evaluated. This has also been very problematic. As Lee said, I grew up in Antwerp. There's a port there. And as an undergraduate, one of the things that we had to study was operations research, and one of the things we had to do is, calculate length of docks where these container ships dock. Filling a container ship is unbelievably hard. They've tried to do this with machine learning, it doesn't work. For the simple reason that every container ship is different, every set of containers on the dock side is different. So you can't really endow the space of all instances with a credible probability measure. And you need that in order to start working with probability theory. All right. So, learning. How do you learn in a Bandit task? Random exploration is optimal. You can do other things. They're equally optimal. You can go left, right, left, right, left, right, or you can do left, 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 right, right, right. That's not random, right? But you actually learn equally much as with random. So is Bayesian updating. Right? Bayesian updating is the best way of doing things. And if you don't, if it's too complicated for you, you can use reinforcement learning. You can use the TD learning, all these things that you know from Silicon Valley. The knapsack task, random exploration, is actually extremely slow. And intuitively, to understand this problem is equivalent to solving a jigsaw puzzle. So I give you, in my bedroom, I have a jigsaw puzzle that a previous owner left in that bedroom of a Bruegel painting with 20,000 pieces. And the guy spent 6 months on that. And I asked the guy, how did you do this? Right? Having spent most of my life in this world, I thought he would have thrown the pieces randomly in the air during 6 months until after 6 months, magically all at once the pieces fit together. Right? Yeah, and if you do that long enough, it will happen. But that's the same thing as saying if I actually throw a tennis ball at this wall, at one point it actually will go through the wall. You know that from physics. You can ask the physics guys over there. But you'll have to do a lot of throwing. And I'll actually show you in experiments what the comparison is between randomly trying to solve this problem and thinking about the problem that is following a particular deterministic algorithm. Bayesian beliefs, this is a little theoretical, this may confuse you if you're not really familiar with Bayesian, Bayesian analysis. Bayesian beliefs, they do converge under your beliefs that you think, this problem is for 75%, the answer is yes. And so I'm going to try randomly and I'm going to update. But there are no objective beliefs against which to evaluate them, so I can't really do very much with that, right? So I can't really evaluate what subjects are doing or participants are doing using Bayesian belief updating, because I have no constraints on their subjective beliefs. Later on, I'm going to qualify this statement. Value maximization. So, in the bandit task, since humans satisfy mild rationality restrictions when choosing between bandits, if the left bandit gives you a higher expected odds than the right, they tend to go for the left. If there are 3 bandits, they're trying to actually also not violate that much transitivity, and so if the first arm is better than the second, is better than the third, they actually will prefer the third one over the first one and not the other way around. And you students do see sometimes a violation like that. But that also means that human choices can be modeled as if value with respect to utility is maximized. And so Nathaniel Dawes' paper in Nature in 2006 shows this with a bandit, multi-arm bandit problem. My former PhD student, Elise Pirzana, we actually showed this also in a 6-arm bandit problem. People are pretty much Bayesian, and they choose as if there is some value function behind them. I should also say, since we are talking interdisciplinary research, economics is based on an as-if value maximization. That's what they want. They want the choices people make at least satisfy some mild rationality restrictions. Because otherwise, their machinery doesn't work. That is, since they believe from class 1, from day 1 on, that people choose based on a utility function that they're maximizing, the choices have to satisfy some kind of rationality restriction. The problem is in this context, it's very easy to find counterexamples of these very simple traditions. So plausible solution strategies, and I'll show you one in a second, they violate basic rationality restrictions, so human choice cannot necessarily be modeled as if value is maximized. It also means that this field of neuroeconomics that prides itself of having found value signals in the ventromedial prefrontal cortex is out. Move over, right? It's got to be something else. I had a slide in there on showing one of these violations, but that would take me a little bit too much time to explain, but we can, if time permits, we can get back to this. This is extremely important for economists. Right? So economists have reacted to this work that I'm presenting today, shrugging their shoulders. Well, you have not proven that value maximization doesn't work here. Absolutely yes, we have proven that. Right? And this is very simple. This uses an algorithm that everybody would use. But I'll explain that algorithm in a minute. This is the question that I wanted to ask. Can we study choice in the knapsack as we do in the bandit task? So as opposed to asking what people are thinking, let's go first to the problem at hand and see whether we can say something about what people are doing from the properties of that instance, the mathematical properties. We have mathematical properties of the multi-arm bandit. Problem, among others, uncertainty. We can measure uncertainty with payoff variance, which is a mathematical concept which exists there because they have objective probabilities. Is it true that when the variance goes up, effort increases, and that if the variance goes up, payoff decreases? And the answers to these two questions are absolutely yes. Right? So you have some predictability, you have some signs that can do it. It starts from the problem at hand, and we don't have to look at what they're thinking. We can already predict their choices from the problem properties. The question is, can you do this here? So let's think about this. What is uncertainty here? Well, first, in the first place, you could think about uncertainty as a difficulty. You know, you may actually look at this problem and say, well, this is a difficult instance. So it's more uncertain. It's unlikely that I'm going to find the answer in the next 20 seconds or the next 4 minutes or something like that. Right? And then the question is, if you can do that, does effort increase in difficulty and does payoff decrease in difficulty, just like here? Right? So there's an analogy. But that raises the issue, what is instance difficulty? Right? And that's where the story starts. So in 2005, two PhD students at Caltech and we started thinking about this. How do you measure a difficulty? All right. Let me just say a little bit more about these sorts of uncertainty in the knapsack task, and I'm going to expand that later because in this slide one important aspect is missing. So since there do not exist objective probabilities that an instance is solvable, the uncertainty is completely subjective. So there is what economists call ambiguity. There are no true probabilities. In fact, it's worse than the usual ambiguity that economists are talking about because there is always some kind of, in their experiments, some kind of true probability. But you can reduce the ambiguity by attempting a solution. You can completely eliminate the uncertainty by using an algorithm that finds the solution. And so I'm going to first look at how people choose, how they learn, what they're doing, relative to algorithms that the computer scientists would say they will find the solution. Then the second one is, the problem is, of course, intractable, which is it may take too much time to find the solution. Right? And I'll give you some ideas what the time is that we're talking about here. We're talking about an enormous amount of time here. Right? So then you go to approximation. At one point you have to then stop searching at a particular, to decide, I'm not going to search anymore. And how do you do that? We do not have Bayesian updating here, so you can't do the standard optimal stopping time type of analysis. You have to use something else. And it turns out these computer scientists over there, the theory guys, not the machine learning guys, right? They have actually worked on this. And that's what I'm going to bring in here. So the question is, what is difficulty? So let's turn to computer science. So this is part of computer science called computational complexity theory. And first I have to introduce the problems in a more abstract way. So most of what I'm going to do today is talk about this knapsack problem. This is the optimization task, which is on the right hand side you have a bunch of items, each with a value. This is now euros and the weights are in kilograms. And there's a knapsack on the left hand side with a certain capacity limit. Here it's 14 kilograms. And with the items that you already put in there, these 4 small items, you get a value of 22. Question is, can I improve on that? By the way, this is deceptively simple, right? So this could take you a long, long time. I had a very smart economist in one time that I was actually giving this in the economics department. And when I showed this, he tossed down all these numbers and he didn't pay attention to what I was saying anymore. And half hour later, he said, I know the solution. Half hour! And he's a very smart economist. And I said, well, really? Didn't you thought it was better to solve this problem than to listen to me? The decision task is what I showed you before. It's a yes-no problem, right? So, can you reach $46 or not? I'll come back to that because most of the theory is developed for this type of problem. It's like an event. Will it rain tomorrow? Yes or no? Normally we put that in probabilistic terms. Well, I think it's 75% chance. Do you know what that means? When you ask somebody, when you tell somebody, oh, it's 75% chance that it's going to rain tomorrow, do you think this person knows what that means? Presumably not. Ecological relevance. This is actually everywhere around us, this type of task. Allocation of scarce resources, asset allocation, shopping, time management, assignment of tasks, scheduling, attention allocation, attention deficit hyperactivity disorder, choice overload, intellectual discovery, putting together something like a battery is a combinatorial task. It's not, the guys who work on batteries, they're not just randomly trying all kinds of things. They actually think about this, right? Strategic interaction, game theory, turns out to be unbelievably hard. If you go to an economics class, you would think that actually it's all obvious, right? It's unbelievably hard. Navigation, next slide I said, it's another problem that is related to this. Actually, it's not the next slide, it's the next plus one. This is just to show that actually economists are starting to become aware that their core problem, which is the consumer problem, the consumer has a budget, £50, walks into Marks and Spencer's and buys, with his £50, among these 5,000 items, a basket of goods, and optimizes. Has some utility function. By the way, if you were to be able to tell your computer all the 5,000 items and all the combinations of the items, what your value is for that. So you give it a utility function, and you would ask your computer when you walk into Marks and Spencer's, tell me what I should buy, given the prices that are out there right now. It's going to take months and months for your computer to find a solution. And that can even be years and years, if not hundreds of years. That's the type of complexity we're talking about here, right? This is not trivial whatsoever. So Richard Gilboa, he was actually an economist but trained as a computer scientist, and Postol and Schmeiler in 2021 publishing one paper, a literal interpretation of neoclassical consumer theory suggests that the consumer solves a very complex problem. That's what's being assumed. That's where economics starts. In the presence of indivisible goods, of course, you can't buy a half car. If you want to buy a trip to Spain, you can't say, oh, give me half the trip. I'll be happy to just be dropped off halfway. You can't do that, right? And you can also see when people are poorer, it becomes more difficult for them because that indivisibility, that makes it gets harder and harder. The consumer problem is, the technical term is NP hard, non-deterministic polynomial. I'll come back to that later. And it appears unlikely that it can be optimally solved by a human. Guess how do you come? Am I allowed to do economics bashing here? Since I am a member of the faculty. They say I'm graced to make this joke, right? Yes, Peter, but we are not assuming that they're actually doing this. They make choices as if they can actually solve this problem. And then my reaction is, every computer scientist would be standing in your office if actually you found a creature on Earth that can do this, that can act as if solving this problem. Because you would actually just hook up the brains to your computer rather than having your own computer solving this. Right? So this is actually a fundamental problem for economics. Right. Here is the other problem. This is the traveling salesperson problem. I'm actually going to come back to that later. So there are some dots. This is like, you have to deliver some pizzas in Cambridge, and you have to find the shortest path to all the customers. Right? I'll come back to that later because I need that for approximation complexity. Definitions. So I'm going to shift gears. This is going to be hardcore math. Right? And when I was at Caltech, I always had to put a slide in with Richard Feynman. So here I put in a slide with Alan Turing. Right? He is basically one of the founding parents of this type of mathematics about intractable problems. So the problems are called NP hard. What does that mean? So I'm going to give you an intuitive explanation, and I apologize to those people who actually understand these problems. So practically it means that the time of the number of computations that you need to find a solution increases more than a polynomial in the size of the instance. And what's the size of the instance? Is the number of items. Or when you actually have to deliver pizzas, the number of clients you have to deliver it to. Right? And I put in parentheses, until someone magically finds a better algorithm. Right? But the general idea about this is these problems, nobody will ever find an algorithm like that, and I hope not, because otherwise I will be out of a job. And it will be even worse. The fact that I'm out of a job is not a problem, but these problems are used in encryption, because it's so hard to solve the problems that you can actually use for encryption, because you know your enemy or the thief doesn't have the time to actually find the solution, right? So if somebody finds a really, really good algorithm, that's going to be a lot worse than ChatGPT, I can tell you. Now, I already mentioned randomly trying solutions is not a good approach. There is a very fundamental theorem about this, but let me just give you the intuition. Have you ever seen somebody try to solve a jigsaw puzzle by repeatedly throwing pieces on a table until the pieces magically fit? Right? You don't do that. So we naturally feel like we shouldn't do that. Humans don't do random solutions either. They think, right? And I'll show you evidence of that. That humans, with the same number of moves, the same number of trials, they do about 10 times as well as randomly trying things out. And monkeys though too. So a former postdoc, Wolfram Schultz's lab, he actually replicated some of our things with monkeys. This is how we look at this. We have humans. This was actually solving these problems together with the market. I'll come back to that later. And here is Bill Stauffer's. This is in press in Nature Neuroscience, and this is a movie that you will be able to get online. I'll just play this movie, and you'll see this monkey, right? It's actually not an abstract problem. It's very closely related. It's called the subset sum problem. So it has to choose a bunch of items up to a certain level, but not above that level, right? Because it goes above that level, it doesn't get anything, right? So the first item is, of course, the monkey goes for a big item that satisfies the constraint, and then the second one has to think, what should I take, right? And the monkey really thinks. So it's a very short movie. Okay, chooses immediately and then thinks. There it is. Very different from how monkeys do their actions in a probabilistic task. They're sitting there and they're just, they're like in a casino, right? Like humans. So they're thinking, and the question is, what's going on there? So I'm going to say a little bit about the hardcore theory. If you don't follow this, or you're not inclined to listen to mathematics, you can just fall asleep for a couple of minutes, right? And I'll just try to keep you with the intuition. But I do want to give you a little bit of an oversight as to what the formal nature is of these problems, because I need to say something about a second type of uncertainty that I haven't talked about yet, which is not the instance complexity, but it's something else. So we're going to focus on decision problems, that is, they have yes-no answers. We consider algorithms. It's a sequence of computational steps that provide a definite stop with an answer, yes or no. So at the end of your search, you're not allowed to say maybe, right? And the question is, what is the number of computational steps, time needed for an algorithm to solve an instance to actually get to say yes when the answer is yes and no when the answer is no. So we focus first on algorithms that always find the correct solution, and later we'll talk about approximation algorithms. A problem is tractable if there exists an algorithm such that time grows at most polynomially in the size of the problem, the number of items in the knapsack, the number of nodes in the traveling salesperson problem. And an example of that is sorting. You can do sorting in polynomial time. Tractable problems are in the class P for polynomial. Now, This is probably the most obscure math that you've ever seen. We're now looking at the class NP complete. NP stands for non-deterministic polynomial. You have to be Alan Turing to come up with a name like that, right? A problem like the knapsack and the TSP belongs to the class NP if a witness for a yes answer can be checked in polynomial time. So it includes problems in P. If you already know that, if you say, okay, the answer is yes, and here is my example that actually, this is my knapsack that leads to at least $46, you can actually check whether it adds up to $46, and that's very quick. No wonder that, of course, Silicon Valley now has the ability for you, if you give it a proof that you think is right, it will check that proof. But Silicon Valley cannot prove a theorem, because that's NP hard. Right? Silicon Valley cannot do the following. Well, I think I cannot do that. Prove me wrong. Right? That is very hard. So you already see this dichotomy between yes versus no answer. Now, a problem is in the class NP complete if all problems in NP can be reduced to it in polynomial time. So they're really the hard problems that can be checked in polynomial time. And these are the two examples, but there are many, many other. The three-set problem, which is a satisfiability problem, is basically proving theorems. Is P equals NP? We do not know. If you know the answer, you can get $1 million for this, which I find is not enough. And I hope nobody will ever find this. That is, can you find this? Translated into everyday languages, can you find a polynomial time algorithm that solves an NP complete problem? Some people use the term NP hard. That's a more general term. Basically, it's the hardest of all these problems. Right? And they don't have to be decision problems. It can be optimization problems. All right, so the reason I actually give you a little bit of the theories for this slide. The classification only looks at the worst case. So I give me an algorithm. I will find a worst case where it's going to take you, the time it takes you is going to be exponential as I increase the size of the instance. Careful, and that's extremely important. The worst case may be different for each algorithm. So one of the criticisms we got to the work is, well, this theory is completely irrelevant. What if in the world out there the worst case never happens? Well, that depends on how many algorithms people use. Because if you all use different algorithms, chances are that the worst case is every time a different one. Of course, you can also immediately see that if you all use different algorithms, you want to talk to each other. Right? But we'll come back to that later. Can we say something about the average case? The problem is, how do we define the average case? Right? So what is a typical container ship that arrives in the port of Antwerp? What's a typical collection of containers on the dock in Antwerp? You can't write a distribution, and you cannot estimate that distribution because it keeps on moving all the time. Right? So can we endow the space of instances with an objective probability measure or an uninformed prior for those who know statistics? This is an obscure part of statistics. The definition of an uninformed prior is, I'll tell you when I see one. Right? And I'm not joking. Right? This is not a very satisfactory answer either. So we need to instance complexity. So we're going to do, this is how we started around the mid-2000s. We actually started from what we thought was a very reasonable algorithm to solve this problem, the Sani-Horowitz algorithm, and we made a metric of difficulty called Sani-K, and that turned out to be, you have to be lucky in life, very useful to understand how humans solve these problems, what their effort they spend, how much time they spend on this. So let me explain the Sani-K, but this is really crucial to understanding the empirical results. I told you what we needed to find is a metric of difficulty, and we thought that as difficulty increases, uncertainty increases. I don't know how long I'm going to have to spend. This is a difficult instance. I don't know how long I have to spend on this one, and after 3 minutes I'm going to give up. Right? Maybe I'm going to spend more time on a difficult instance than an easy instance, just like with bandits. In analogy with bandits, If the bandit has low variance, I spend less time on it. If it's high variance, I spend more time on it. So we start with the knapsack optimization problem. So you need to fill the knapsack and try to find the maximum value. And you start with the greedy algorithm. What is the greedy algorithm? It's not the greedy algorithm that you know from TD learning or something like that. So from reinforcement learning. Actually, this is the computer science version of it. So what you do is you rank all the items in terms of how much value relative to the weight. Right? So the density. And you rank them, and then you fill the knapsack in the order of value over weight. So first the item with the highest bang for your buck, as they say in American, and then the second one and the third one until you hit the capacity, then you stop. Right? So this is the greedy algorithm. And I should also add to that, this algorithm can be arbitrarily bad. You can easily write down examples where it can't even find 50% of the total value. Because the pivotal item, the item you can't put in there, may be very, very big, and yet produces the correct solution if items are infinitely divisible. That actually algorithm is the correct one if you think the world is infinitely divisible, just like most of my colleagues in economics, by the way. They think that you can buy a half car. And that's not a joke, right? They basically say, well, the way you can buy a half car is you share a car with somebody else. And I say, why don't you see people do that then? Right? Some people do that, but not many people do that. Well, moral hazard and all that. Right? So, long story. If the greedy algorithms gives you the optimum, then it's an easy problem because you can find this very easy algorithm, which is you don't have to think about this, right? You just have to rank order. People are very good at rank ordering, right? We call that an easy one, and Sonic A is 0. These are the easiest ones. You'll see later when people do that, they tend to use the greedy algorithm. When they see a problem, an instance, that actually has Sonic A equals 0, they tend to start with the greedy algorithm. Wait a minute. How do they know that Sonic A is equal to 0? Because you have to know the solution before you can figure out whether Sonic A equals 0. So let's go to the next thing. If the greedy algorithm doesn't give you the solution, then what you do is, you pick one of the items that the greedy algorithm didn't take, at random, you put it in the knapsack, and then you start the greedy algorithm. And then you try all the singletons, all the items you could start with that you put in there, and if you find then the solution with one of these items and then the greedy algorithm, Sonic A equals 1. If that doesn't work, you go one step further, you pick two items that the greedy algorithm didn't put in the knapsack. You throw them into the knapsack and you start the greedy algorithm. Right? If that finds a solution, Sonic A equals 2. And it continues like that. 3, 4. We have gone actually up to 10 items. Sonic A equals 4. What does that mean? You can't do much with the greedy algorithm because you have to already put 4 items in the knapsack before you can use the greedy algorithm. So if you were to start with the greedy algorithm, somehow you have to throw 4 items out. How are we going to do that? Right? We have to add 4 items. It's not going to be easy. And actually what's so surprising is when Sonic A equals 4, virtually nobody starts with the greedy algorithm. So somehow people have already, despite the fact never ever taking a combinatorial mathematics class, this is a difficult instance. Right? And despite the fact they don't know the answer, they already know that actually this is a difficult one. I'll come back to that later. So we get to the humans. We get to the interesting part, how humans choose under computational complexity. Until now, the only thing I have done is showing you that there is a framework in which to think about what people are going to do, how they're going to choose, based on a concept of uncertainty that's related to difficulty. And we're going to do what's equivalent to what you do in a bandit task. If the bandit problem gets more difficult, according to probability theory, people are going to spend more effort and their performance is going to go down. We now have a candidate metric of uncertainty. It's called Sonic A. Is that going to work? Well, we don't know. How did we know that variance worked? Well, you had to test it, right? Could very well be that people were not interested in variance. That people are just not into probability theory. They're doing something completely different. By the way, probability theory wasn't really seriously developed until the beginning of the 20th century, right? And then maybe a bunch of French mathematicians like Laplace in the 19th century, right? So there's no reason to believe ex ante that actually probability theory would work. Another way to say it is before 1945, before Alan Turing and other people, these experiments, we couldn't run them because we didn't have a metric of difficulty. We didn't have Sine K. We didn't have also the link with uncertainty. All right, so question one, how often do humans find the optimum? So we're talking now about really, can they get the optimum? So here is one experiment. We have multiple experiments. This is the one we published in Scientific Reports in 2016. Here you see we have 8 instances and we have 20 participants. Each participant gets to solve each of these instances twice. So we start with one participant, instance 3, then we go to 6, we go back to 3, 2, etc. So we basically randomize across participants. And all these problems they're like the ones that you saw before, pretty much 10 items, right? So that's the size of the problem. We're not talking about going shopping in Marks and Spencer. We're talking about a much easier problem. What's the average success rate? What's the chance they find the optimum? Less than 50%. The dashed line is 50%. They're that difficult. How much time do they spend? No more than 4 minutes. Right? So they tend to go up in 3.5 minutes. And that will depend, as you'll see later, on the difficulty. There's this one instance 7, that only 2 participants so far of the hundreds that actually we have tested have been able to find the answer to. One was a Caltech undergraduate, not surprising. The other was University of Melbourne undergraduate. The interesting thing in both cases, the second time around when they actually had to go resolve the same instance, they couldn't find it. Talk about bad episodic memory, right? Compare their performance though, these are the blue lines, right? So it's about, it's close to 50%, but below 50%. Compare that to the expected performance from random search. I'm solving my puzzle by throwing pieces in the air. I'm trying to randomly fill this knapsack, right? And if it doesn't work, I'll just throw everything out and try something else. Right? So assuming the same number of full knapsack visitors as any of these participants, it's 10%. Right? So they do about 5 times as well as random search. They are not randomly searching. They're thinking about this. Across participants, there's an enormous amount of heterogeneity. There are pretty bad guys out there. And then you have pretty good guys. The person who solved the 7 is not necessarily one of the best ones. Right? The key question is, does their performance go down with the difficulty, with the Sine K, which is almost as computer scientists will say, well, this is an arbitrary metric because it relies on a particular algorithm, the greedy algorithm, and the Sine-Horowitz algorithm. But the answer is yes, and it replicates very well. So this is in the middle, the experiment that I've just showed you, but it replicates very well. Right? So we have 2 other experiments there. So we're talking about a couple of hundred people here. And as you can see, as Sine K goes from 0 to 4, the performance goes down. How much depends on the situation. We can talk about Sine K equal to 1 later on, because you see there's a dip and it always occurs. Right? But let's not get distracted by that. Why is this surprising? First, the theory we covered so far is focused on algorithms that do find a solution. Right? So this Sine-Horowitz algorithm finds the solution. And humans do not always find the solution, actually less than 50%. So why would this theory help her? You should actually go straight to approximation complexity. Yet we find a relation between instance complexity in 1 and 2. Right? And we have an answer to that, and it's related to this here. So this may be a complicated graph. I'm going to show you, this is one instance, and we had these 20 participants, each solving a problem twice. So we're going to see is 40 trajectories through this network. This network is a visualization of the space of all the knapsacks that you can get. On the x-axis is the value of the knapsack. You start out at 0, there is nothing in the knapsack. And then as you add items, the value goes up. The maximum value is here. That's where the blue dot is. So that's the x-axis. Going to the right increases the value. The y-axis, the vertical axis, is the distance in items, number of items from the optimal knapsack. You start out with nothing in the optimal knapsack. This is a knapsack with 10, where you have 10 items, and the optimal solution has 7 items. So if there's nothing in the optimal knapsack, you're 7 items away from the optimal, right? And that's where you start out. Everybody will start out here. 0 value and 7 items away from the optimal knapsack. If you are incredibly smart, what you want to do is add pieces, to this items to the knapsack that get you straight to the blue dot. So that the first item you put in there, you're 6 items away from the optimum. The second one, you're 5 items away from the optimum. The third one, you're 4 items away from the optimum. So you want to be on the contour, the outer contour of this map. All the other dots that you see there with all these crosses are all knapsacks that you can visit on the way. So you could actually do the first item you put in there may be wrong. It doesn't belong there. What happens, since you add something, the value goes up to here. But now you're 8 items away from the optimal knapsack because the item you put in there, you should take it out again. You can actually do even worse. You can put a second item in here, right? And you're very excited because notice how much the value goes up. The problem, it's wrong. You have to take 2 items out. So you're now 9 items from the optimum. So you have to go back. And these are big steps that you have to set back, right? So I'm going to show you the paths that all these people take. And you'll immediately see a very striking effect. You can see that they're thinking. Some of these guys get stuck at one point and say, well. And then all at once they just move back and they move up. Like the red guy here is stuck and is thinking, my God. And now he realizes, yeah, that was a big step, but I should take it out. Right? And he gets up all the way to not the optimum, but he gets very far. But he's struggling. You can see this, right? He's frustrated. Now there he is. But actually, he's still not decided whether he was really... So you have to take out a lot of items in order to actually get to the optimum here. So here's a statistic. In this particular problem, if you measure the number of full knapsacks that they visit that are possible here, knapsacks that are filled to capacity, you can't get any further, each of them visits about 3% of all the full knapsacks. 3%. Collectively, almost half, 50%. Right? So humans are fantastic. So this is basically what I told you before. You will all follow a different algorithm. In fact, actually, the next time you do the same thing, you're going to follow a different path. Right? So you can immediately think, okay, well, that's actually an opportunity. We need to start communicating. And that's where our first experiment actually started. We need people to communicate. Heterogeneity is dramatic in this. If you ask your computer to solve this problem, it always uses the same algorithm. There are some more advanced algorithms nowadays that will switch between 3 or 4 different algorithms. But it will always basically follow the same path. So there is no diversity. And we talk a lot about the benefits of diversity. You can clearly see this here. So what we did is, you need people to communicate. I'm an economist. I don't believe in people communicating. So we set up markets. And markets actually help a lot. This, of course, also kills off part of economic theory. But that's a long story. So Deborah Melosso and Yannickovich, two economics PhD students at Caltech. They're now in France. They and I actually just worked on this, and we published this in Science in 2009. But economists are still puzzled about the whole thing. Yes, markets help. Question 2: how well do humans approximate? Right? So they don't really find a solution. How well do they approximate a solution? So now we're talking about the value of the knapsack they reach relative to the optimum. Note, this is actually a very puzzling question that you have to ask this in 2023, because First King Kahneman's their famous science paper in 1974, which has become the core of behavioral economics. It's the beginning of heuristics and biases program. They basically argued, this article shows that people rely on a limited number of heuristic principles, i.e. algorithms, which reduce a complex task, without defining what complexity means, the complex task of assessing probabilities. This is actually about probabilities and predicting the values to simple and judgmental operations. The question that you should ask is, are the heuristics adapted to the complexity of it? And so we're trying to answer that here. The focus has been on probabilistic tasks rather than the really complex task, the combinatorial task, and so that's what we are doing. Another important remark is, economists tend to tell me, I'm bashing economists again, right? So they tell me, well, you know, we don't care that they find a solution as long as they approximate the solution well. That's what they're doing. Well, so my reaction is, how do you know that? Well, especially because of this here. For some problems, approximating the solution well is as difficult, as time-consuming as finding the solution. It's actually the class NPO. They're not polynomial approximable problems. So you can't do a very good job. So what you do is you run an experiment, or you actually have some of these. Now, the theory is for what we call Turing machines. These are these special abstract computers. This is not for biological computers, right? So they have a mathematical definition of what a computer is, which is inspired by your electronic computer. They're not talking about neurons and all that stuff and networks, right? They're talking about a computer that has a hard disk and a few other things, right? And so we did this in the traveling salesperson problem because you can actually embed these these three classes of very well approximable, not so well, and not approximable ones within one graphical interface. So this is a traveling salesperson problem. The basic problem is, you see all these dots, right? Can you find the shortest path that connects all of them, right? And there are two versions of that. There is a version where actually the paths satisfy Euclidean geometry. That is, if you go from A to B, that's shorter than going from A to B through C. The non-Euclidean one, you would say, well, we live in a Euclidean world. No. Actually, we live in a non-Euclidean world because it could be that from A to B is a congested road, and it's actually faster to go through B. Right? So you get a lot of non-Euclidean stuff as well. The most difficult ones are the non-Euclidean traveling salesperson problems. They are not approximable. The Euclidean traveling salesperson problem is okay, but for every level that you want to reach, you need a different algorithm. And then the fully polynomial approximable ones, where there's an algorithm that you can build that gets closer and closer to the optimum, is actually not directly a traveling salesperson problem, but it's your Google Maps problem. I need to go from start to end, and I need to find the shortest path. Right? So you ask Google, how can I walk from here back to Cedric's site? Right? And it will just compute that. Silicon Valley always picks the easiest problems. Right? So they can, this is the easiest approximable. So you can actually approximate this very well, and they can solve this problem in a very short period of time. Question is, how do humans do? Right? Can I use this classification, which is a classification for Turing machines, for humans? And the answer is absolutely yes. Right? So you see on the left-hand side there, approximation performance, that is, what is the percentage, how much value do they reach? And as you can see, the WCSPP, which is this Google problem, they're actually pretty good. You don't need Google Maps. People are pretty good at finding their way. from A to B in the shortest way. So Google is pretty much useless. You should people should spend more effort on it. Then when you go to the Euclidean traveling salesperson problem, that's already more difficult, and you can see people are significantly worse now. Right? It becomes a lot harder now. You have to connect all the points. There's this delivery guy on his little bike, right, and it has to drop off 5 pizzas in 5 different places. What's the shortest path? And then the worst one is the random TSP, and you can see they reach 70% of the maximum. So it's exactly as the theory predicts. Right? There are other things on this slide, but in the interest of time, I'm not going to go over them. Why is this not surprising? The theory is again based on the worst case in a class, but the worst case may depend on the algorithms used. And since humans use vastly different algorithms, or solution approaches, or heuristics, the worst case analysis effectively becomes the average case. Even if the meaning of average is ambiguous, right? So, as I already pointed out, and we have done simulations, we have done analysis to support this. I have 3 minutes, so I'm going to just basically say we have done some imaging studies on this, and there you need to take into account another dimension of uncertainty, which is once I've found, so we have a decision problem here, decision variant. Once you've found that the problem has a yes answer, you found a witness, then all the uncertainty is gone. So even if you start with a very difficult problem, so ex ante, the uncertainty was very high, ex post, once you find the solution, the uncertainty is completely gone. And I'm going to show you only one slide that shows you how the dynamics in the brain works. So first, so I'm not going to go through this. We can talk about this in the next half hour if you're interested. So this is our scanner, 7 Tesla, big machine. Melbourne, the Australians spend a lot of money. Now they're going to spend a lot of money on nuclear submarines. So there are 3 brain regions that show up here. You can guess this, right? So this is uncertainty, effort, and calculations. Anterior insula, anterior cingulate cortex, angular gyrus. Right? This was not surprising to me. This was a hypothesis we had. Right? But the question is, what is the connectivity? What happens? How they are talking to each other? And so here for anterior insula, dorsal anterior cingulate cortex, and angular gyrus, look at the top charts. Right? And what I'm going to show you is first the green line. The green line are these instances which actually have minimal uncertainty. Why? Because ex ante they're easy, and ex post the answer is yes. And what do you see? Anterior insula, you see the uncertainty building, and then it goes down. Dorsal anterior cingulate cortex, if you're thinking about effort allocation there, but that's not exactly correct if you actually look at the details. It also is much lower. Angular gyrus, you stop calculating after a while because you found the witness. And we see the green line going down. Let's look at the other extreme, the blue line. It has maximum uncertainty because ex ante, it's very difficult. So it has high sign k, so to say. And ex post, it's very uncertain because actually the answer to that question is no. And to prove that the answer is no, you pretty much have to list all the possible cases. It's like when a mathematician that you have as a poster comes back to you and says, well, I can't prove your theorem. How do you know that you spend any effort? You have to do all the work yourself. Right? And you see then with the blue line, you see this in anterior insula, this uncertainty signal maxing out just before you have to make the choice, yes or no. Dorsal anterior cingulate cortex, you're still trying to figure out what's going on. And angular gyrus is also at the highest at the end. Right? So now you try to understand these dynamics. You can't use standard dynamic causal modeling or something like that. You can go to Granger causality or something like that, and you find interesting things. But I should stop here and let me just conclude with these remarks. We've shifted the empirical paradigm from finding what people are thinking to our effort and performance adapted to uncertainty at hand. And what is uncertainty? First, instance complexity, ex ante. Most of my talk was about this. Second, uncertainty is satisfiability, what the mathematicians call proof hardness. So it's ex post. The answer to the question is no. Well, how do you know it's no? Maybe someday somebody will find an example that actually the answer is yes. Humans choose as if they were abstract computers. So this theory was developed for abstract computers, for Turing machines, applies to biological computers like us. And I would even challenge maybe monkeys, and I don't know how far you can work on an animal model of this type of problem. Humans implement approximation algorithms, or heuristics, which are subject to the same laws as that of abstract computers. Approximation complexity works. Uncertainty related to these two sources of uncertainty drive dynamic neural interaction in a triangular system, anterior insula, anterior cingulate cortex, and angular gyrus. By the way, there's another part of the brain that actually is significant in the whole brain analysis, but I think it has to do more with frontal eye field, people adjusting their eye gaze. Heterogeneity in solution approaches suggest communication is productive through, for instance, markets. So there is work to be done for social science as well, and that's it. I should stop here.
Lovely. Thank you very much. Okay, so as is traditional, we'll have a short transition. So if you want to make your way to another event, feel free to leave now. Otherwise, stay for half an hour questions.
Yes, but sure, I'm around. I'm now at Cambridge. Right.
Okay, anyone like to open the question? Deborah?
So as an experimental psychologist, I was just struck by your comment about I'm not going to ask people. And it kind of seems like you're going about it blind, like you don't really know mathematically how to do it, how to define it. There's so many. It's not like mathematicians have got a solution and we're just no. Even defining the uncertainty is hard. So
Why did I do
ask
that?
people.
Why not ask?
Why not figure out some ways that they do it and maybe see if one way is better, or if you're clever, whether you implement something differently? Like what?
It's a little bit out of frustration. We're trying to figure out what they're really doing and asking them what strategy do you use, because they cannot express what they're doing. They can expose, come up with all kinds of rationalization. And this is probably related to the heterogeneity that I showed you. Not only that I showed you is the heterogeneity across people. When I give you the same instance a second time, you actually approach it in a different way.
That is the systematicity to it?
Was it?
Like, do we know that they can't express what they're doing?
That's a good question. I can't get that out of them. So it could very well be that there is a protocol that you have to use here in order to actually generate the right answers. But I don't know what it is. Right? So that's why we went to the approach that you use for probabilistic tasks, where nowadays people don't ask questions, they just observe what they're doing, right? And it's almost, because there, you can use a lot of different approaches because the random search is optimal anyway. Here, of course, at one point, we really want to know what they're thinking, and in particular because of one of the things that the biggest issue what the results here is the fact that they see this problem and they can already figure out within a couple of about 30 seconds whether the instance is difficult or not, whereas I as the experimenter cannot without knowing the solution, right? So there is, the question is where did they get that from? We can start asking questions. What are you looking for? We have done eye tracking. The data are a mess. We have looked at their first full knapsack. Turns out to be extremely important to know what they do, but the first full knapsack is What else have we tried? We've tried all kinds of things to actually get at what are they thinking. And at this moment, we don't know what it is, but there is an issue. The computer scientists are very interested in figuring out why it is that humans, within 30 seconds, can figure out whether an instance is difficult, because they cannot.
Can you maybe give an example of what people say when you ask them how they're trying it or how they figured out it was difficult?
So when we talk to them afterwards, right, you get vague results like, oh, this was difficult, or we thought this was an easy one. And then you ask them, why do you think it was an easy one? Well, look, you ordered this, you filled it, and it looked like it was right. Of course, this is also my problem as a researcher coming out of economics, where we're not used to asking people questions. We don't know how to ask questions. Economists are now into surveys as well, asking people questions, but that doesn't come naturally to us. So, this is why interdisciplinary research is important, right? But I can tell you, this type of research started by asking people questions, especially in the traveling salesperson environment, and it has given us some ideas to where the easy instances are and where the more difficult ones are. But they're kind of the obvious ones for computer science as well, whereas in an abstract problem, it's not obvious whatsoever. Right? So that literature kind of got stuck. And so we basically then put the horse behind the cart, if you wish, and let the horse push the cart. And we looked at let's start from what's the problem that they're trying to solve. Right? A little bit like visual research. The first question you have to ask, if you want to understand the visual cortex, is what is the brain trying to solve? And is it a difficult problem that they're trying to solve? Right? And out of that comes, vision is not to see. Vision is to get rewards or whatever. Right? So yeah, I'm sympathetic to it. I make very strong comments here, right? So I'm an economics passion and so, but I think in talking across disciplines, it's important to be aware of what our advantages and disadvantages in each of the disciplines are, and where we can make progress because we're actually attacking the same problem from a completely different angle.
Thank you.
In terms of the area your research in finance, economics, or even computer science, and what's your basic research philosophy? And in your worldviews in your research, what do you will do and what do you will not do?
If I may make a very grandiose statement, I think I'm a scientist. I just want to understand what's happening, and whether it's economics or psychology or neuroscience. You just want to understand what people are doing. And I'm particularly interested in computational complexity for the simple reason, and I think that is something that humans are way ahead of computers. You cannot. Silicon Valley cannot do this, right? They don't have machinery for that. They have machinery for probabilistic tasks, but they don't have machinery for. They're not competing with mathematicians yet. I'll give you a very pointed example of that. So remember that AlphaGo beat the human on the game Go. This South Korean, he was a master, 40 out of 15, the machine won. It just took a couple of years and a second-rate Go player in the US to beat these programs, 4 out of 5. Why is that? It becomes at one point a combinatorial problem to find a way to surprise this machine with something that the machine had never seen before and got distracted by it. And that any human would see the strategy that this guy, this young chap in the US followed, you would not fall for this one because you would recognize immediately a pattern in it. And I think that has to do with this computational complexity that we're pretty good at. And you see monkeys as well, right? So what is striking, I think, is that we don't teach this stuff in schools, right? In fact, it's even worse, right? When we use Google Maps, when we want to go from A to B, no, that should be forbidden. What we do in school is we do a lot of rote learning. We give them problems which are probabilistic, stochastic. Yeah, we cannot beat machines for that because machines use the same algorithm that we do, but they're just much better at it. And they're much more persevering. They actually explore a lot more than humans do, right? But the complicated problems, the complex problems, that's where humans are good at. This is related to creativity. Creativity is combinatorial complexity. Right? If somebody comes up with, wow, this is fantastic, I've never thought about this before. It's not that this person randomly picks it out, they actually found a combination that is perplexing. Right? And we don't train people. So one of the questions that we've asked a lot is, do you see any improvements? So we did a clinical trial with 3 drugs, Ritalin, modafinil, and Adderall. So methylphenidate, modafinil, and dextroamphetamine. Right? Those 3. We did this within a person, 4 weeks, and on placebo. Right? So randomized, and you know this. So you show up 1 week, you get 1 pill, you have to do these tasks. Come back next week, get another pill, you do the tasks. Exactly the same one. Right? So we don't give them different instances, right? And then the 3rd week, and then the 4th week, and then you try to figure out that after 4 weeks, that actually they sit there and they do this very quickly. Absolutely no learning effect. Does that mean you can't get better at it? I don't believe that. I think you can get better at it. Right? There's another problem out there that people actually solve for fun, which is Sudoku. Right? It's very much related to these problems. Do people get better at it? Yes, but how do we get better? Can we actually teach this? Should we actually force everybody in school to actually get better at things like that in order for them to get better at solving combinatorial problems? Geometry is proof theory is taught for people to think about combinatorial problems. If you go a little bit further in mathematics, the same, proof theory is, proofs of theorems are it's 3-side problems. So it's all in the same category, but a lot of students shy away from it. Well, that's too hard. Right? Much easier to just go to a casino and randomly try out things. Yet on the art side, that's where you see the creativity almost. Without actually realizing they're doing the same thing that the mathematicians are doing. Right? Researchers are doing it. Right? When you get your PhD, you have to think about combinatorial problems. You're not thinking about you're not a rat that uses reinforcement learning, right? Getting a PhD is not a question of trying it 100,000 times and finally your advisor signs off.
Can I ask a follow-up, kind of related to Deborah's question as well? In the you said that one way of getting people to improve was getting them to work together.
Yes.
And in Bahador Barami did some experiments on this kind of thing with more probabilistic tasks, and then you also see people improve when they share information in those tasks. It seems like people are sharing information about their uncertainty estimates.
Yes.
So in your case, when you have a marketplace, what information are they sharing?
Well, this turns out to be extremely, the market design is extremely important. So we have a very long, thick paper about this. Because we tried several market designs. And again, we went back to computer science. There is a part of computer science that's called oracle theory. So where you take one of these problems and the question is, can you give a message to the solver so that the solving procedure protocol becomes much more efficient? Or in other words, in terms of approximation algorithms, can you give external information so that you're more informed about when to stop, right? Or you stop too early or something like that. And we found market designs that do a very good job. And so one of them is, take the knapsack problem, optimization problem. The design that works extremely well is you have one security where that pays the value of the optimal knapsack, right? So you get endowed with a few others get endowed with a few of these securities. I get nothing. I get the problem. The only way I can make money is if I start trading. I start solving the problem and start trading. And I find out that, let's say you the price of that security now is $40, so people expect that the maximum value of the knapsack is $40, and I find that actually I find a witness for $45, I go and buy. Right? Economists would say this is not going to work because you're going to go in the market and you're going to reveal that actually it's more, so you're not going to make any money. There will be no trade. That's absolutely not true. And that has to do with the combinatorial complexity rules. They don't take into account. But anyway, let's continue this. If you have this single security, right, the prices zoom after a couple of minutes to the true value, optimal value. And on top of that, what's absolutely surprising is there are no bubbles. This is not cryptocurrency. This is not Bitcoin. Right? So in fact, actually, very little effect of you going, once you go above the maximum, it comes immediately back to what the maximum is. And that's, the market operates like an oracle. The people trust the market because you can also see, the analysis we did is, imagine we can actually track where people are at any moment in time. We can, in the interface, see what is their value that they think the knapsack has, given that they put some items in there. Let's say that I think it's $42 and I see the price is going up to $45. I go back and I'm trying to find something that actually gets up to 45. If after 20, 30 seconds I can't find it, I'm selling. Right? So you see this interaction with the market. It's absolutely fascinating. They don't talk, but they trade. They talk with the market. Right? They act with the market and it works extremely well.
Can I have a question?
Yes.
Well, based on some of the statements that you had there, I would like to ask you what you think is the ecological validity of your paradigm, because to me it's a very artificial task. We don't solve problems like this very often, and possibly the fact that you see almost random starts in terms of strategies within individuals and across individuals suggests no learning, which is fairly unusual, and that's what's suggesting to me that it's a complex artificial task that is very difficult to generalize to real world situations and consumer behavior. Can I ask you what you think about this comment?
Well, I don't think that is an artificial task. I think a lot of tasks that we have to solve are of this kind in the real world. Now, how we solve it is a different matter, but don't you go shopping every day?
Yes, but I do not work with the level of complexity you've got, right? So the manipulation of difficulty in your paradigm.
I try to argue that, in fact, the task you have to solve in real life are a lot more complicated than we have.
Sure, but I allow for learning and habitual behavior there.
There is habitual behavior, but the question is if next time you've never gone to Sainsbury, you have to start from scratch. So the question is, how do you approach that?
Well, I use conserved knowledge, right?
But where do you get that knowledge from? If let's say you get a job, you get a new job somewhere, right? And you have to schedule your day. You're in a new environment. You do have to think about it. It's related to ADHD as well, right? So one of the things that actually, when you talking to clinicians who actually have to deal with ADHD, one of the ways you can figure out that a kid has ADHD is by just looking at the knapsack that they take every day to school. And there is completely useless stuff in there. And that you ask the kid, why did you put it in there? Well, I don't know. You are solving these problems a lot more than you think. And there's a second point that you made. They do not start at random. I didn't have time to...
No, I'm not suggesting that you wouldn't start at random point. I'm suggesting that you would need to see some sort of learning from your past experience. Otherwise, it would be...
Why? This is very hard to define learning in this particular context, right? So how would you test that people are learning except by looking at whether their performance goes up? Right? And I just told you that we don't see much of an effect in this very short period. Right? The experiments still have to be run. I completely agree with that. But when I give you, for the first time one of these tasks, the first full knapsack, way before your final solution that you submit to me, allows me already to predict very much where you're going to find the solution. And this is what it's also interesting about these drugs. When you're on the drugs, right, then you become a lot more random.
I wouldn't mix it with the clinical population and
No, I'm not talking about clinical population, right? I'm talking about healthy individuals.
Just clinical population. ADHD is.
You know, but I'm talking now about giving drugs to a healthy population, right? So you give Ritalin to a healthy population, right? And the effect is that this first full knapsack that you get there is not anymore of the same quality of what they had without. So there are some systematic effects there.
Yes, well, I can just rephrase it. How do you think it generalizes to real life?
Now we can talk about this. I get these, already 20 years. This comment from economists, right? So when you run an experiment, what does this have to do with the real world? Let me give you a very blunt answer. This is science. At first, I want to understand whether I actually can find a theory that explains what people are doing or monkeys are doing in the lab, and then let's talk another time about how this relates exactly to the real world. My claim is that the tasks here are abstract representations of things that you actually have to do in real life. Just like when we run a multi-arm bandit problem in the lab, this actually has to do something with real life. You have to make decisions as to whether you're going to go right or left in a stochastic environment. Right? I think I can't argue any more than that.
Yeah,
right?
no, that's fine.
Right.
Thank you.
Yes.
So you had a question first.
I was curious why people seem to be doing worse on the Sine K1 problems compared to the Sine K2.
Yes, okay, that's a very good question. So I do not have an answer to that, but I have a conjecture. And the conjecture is, as I said before, they seem to recognize sine k equals to 0, and they start with a greedy algorithm. Now, when I give you a problem with sine k equals to 1, you can very easily confuse it while, the greedy algorithm works. Right? And so they start with the greedy algorithm and don't think about this anymore. Going back to the question of before, we should have asked it, right? But I think this is between sine k equal to 0 and 1, there's a lot of confusion. Especially because the way you can go from sine k equal to 0 to 1, one of the things you can do is you can increase the correlation between values and weights. And so people get more confused, right? The design of this experiment, there are some things that are very, very important. One of the things that we needed to get across all the sine k's is that if you use random search, you would not see an effect of sine k. That is, a random search would do equally well at sine k equal to 4 as 0, right? And maybe that's what generates this. So I can't give you a definite answer, but I have possibilities that need to be explored.
Just to go with my children have ADHD, but that's not my question. It's really just a clarification. You've said sometimes that people can do something here, that your human participants are doing something that machine learning and computers can't do. What is that? Is that the knapsack task?
Knapsack task, yes.
They can actually solve the problem faster or more efficiently.
Computers or humans?
Than
No.
the computer.
So, in a computer, there are two versions. There's machine learning, where you randomly try things, right? And then you have algorithms. You go to the Department of Operations Research, right? What they work is on algorithms that actually solve problems like this, logistics problems, filling container ships. They do not use machine learning, right? Because they know that if they do machine learning, of course, machine learning can do this as well, but it takes a lot longer than, and long means an enormous amount of time. If you have a container ship with thousands of containers in it, and there are 10,000 containers in the dock.
So you're saying what you're saying is that humans can perform artificial neural networks, but they can't outperform
With the same capacity.
computer algorithms.
Yeah, with the same capacity. Right? So if you were to give the computer the ability to try an equal number of times as a human did, the machine learning guy doesn't do as well.
So you're assuming that when you can measure what people are trying,
Yes,
by
because
what they actually
Yeah, well,
because
there is
can't
a-
they think?
so we used also eye tracking. Right? So there are people who sit there and you can see they're not moving. I showed you this picture, right? So
Maybe they're not moving because they're thinking.
they're thinking, yeah, and I have no idea, and I didn't ask them, are you thinking? No, we just presume that they're thinking. The monkey experiment is very good in that because the monkey experiment, if you make a choice, that's it. You can't go back to it. Anyway, that's a little, I think. Yeah, the statistic is the following: that if you only look at the moves that they're making, and you let the machine randomly pick based on the same number of moves, the machine is only 1/5 the has a performance which a probability of finding the solution which is only 10% as opposed to 45% in the instances that we gave. And on top of that, it has no relationship with sonic key. So you cannot explain why with random algorithm why there's this relation with sonic key. Let me actually
just talk about choosing
explain this in a
random.
different
You talk about choosing randomly rather than
Yeah, yes, I understand. So, well, choosing randomly and machine learning uses. We actually have worked on trying to figure out some of the statistics of this, right? Imagine that you actually set up a reinforcement learning algorithm with this, where you can actually keep track of the running maximum. You try randomly, but you keep track of everything that you've done in the past, right? And then compare that to, and see how much time it takes. But let me give you another example of this. So first there's a hardcore theory. It says that if you can find a certain performance with a random algorithm, you can always replace it with a deterministic algorithm, and you can get exactly the same performance. So you can always beat a reinforcement learning guy who randomly tries all kinds of things with an equivalent deterministic machine. That's the first thing. The second thing is, one day I was in an operations research department in Toulouse, and I had fun going around and asking people what are you working on. These guys are working on logistics problems, right? So Airbus and all that stuff. And these are all NP-hub problems. And they're very well aware of that, and so I asked them what algorithms they use, and in each office I asked, why don't you guys use machine learning? And they start laughing, it's not working. I said, well, have you tried? Yes, we have tried, but it doesn't work. Right? And then I asked them, do you have a theory that actually underpins this experience that you have, that machine learning is ineffective here? And they said no, except for that one theory that I was talking about. Right? So this is an empirical observation. Can I prove that machine learning will never be able to beat algorithms, deterministic algorithms? No, that does not exist. There is, in probability theory, a very deep result out there, which is not machine learning, but it's Bayesian learning. And it's a paper by Diaconis and Friedman in the early 80s, 1983, in the Annals of Probability, or the Annals of Statistics, showing that Bayesian updating generically will fail if your parameter space is too high dimensional, and that's the case here, because we're talking about the parameter space being all the combinations you can have, right? So if you have 10 items, to do 10 possible cases. And that is actually telling you that machine learning is going to be have to stop when the cursor dimensionality starts setting in. But when you have simple problems, it should work. I don't know whether this is a satisfying answer, right? It is just giving you suggestions as to why this is a completely different type of environment. Right? Okay. I make the contrast starker just to, for the sake of the argument.
Cool, okay, I think we better wrap up there. We'll maybe see if we can satisfy that further over a beer.